Example 41. For a circular conduit of diameter 3.6 meters, compute the specific energy for a flow of 3.4 cubic meters per second at depths of 0.6 meter, 1.2 meter, 1.8 meters, and 3 meters, assuming alpha is 1 in alpha velocity head. 41.2, estimate the critical depth where E is the least. So that's the technique for this circular section or channel. The critical depth occurs where specific energy is minimum. Then compare Q square over G and area critical cube over B. This is the supposedly equal at the critical depth if they are satisfied. So they are not necessarily equal because of rounding of values, but they must be close. Then if n is 0.015 and slope of the bed is 0.002, find the normal depth. Normal depth is the depth corresponding to uniform flow. Then at this critical depth and at this normal depth, we make sure that they will not cross the range of depths where we find the distance between changes in depths, because that's the next question. Find the distance in one reach between depths of 1 meter and 1.2 meters, and find also the distance in one reach between depths of 2 meters and 2.1 meters. So this is a very comprehensive problem, so it will require longer solution. So let's generalize everything. Let's have the figure. So I have here the case where the depth is shallow, below 0.5 of D, or 0.5 of 3.6, below 1.8. So the radius is 0.5 of the diameter, and the other one is above. So let's check if the formula will change or applicable from bottom to top. First, for the area, it is area of sector. I denoted the angle here as theta. And so area of sector is 1/2 0.5 radius square central angle in radians. So if that is in degrees, we must multiply that by pi over 180. Minus area of triangle, which is 1/2 product of adjacent sides times sine of the included angle. So 1/2 of quantity 0.5 d squared, then the central angle must be in radians. So if it is in degrees, we must convert that by multiplying pi over 180 degrees. Then minus area of triangle 1/2 0.5 d square sine of theta degrees. Simplifying, factor out 0.5 d square over 2. Then we have d square over 8 quantity pi theta degrees over 180 minus sine of theta, where theta is in degrees. Then for the angle, for the case where it is above, so it is area of big sector 1/2 0.5 d square theta pi degrees over 180 plus area of this triangle, where the angle here is 360 degrees minus the angle here, 360 minus theta. But if we expand sine of 360 degrees minus theta, sine 360 cosine of theta, sine 360 is 0. Then minus cosine of 360, which is 1, cosine of theta, so sine 360 cosine of theta minus cosine of 360, negative 1, cosine of theta. So this is negative cosine of theta, or sin sine of 360 cosine of theta plus cosine 360 sine of theta. So area will still be pi theta degrees over 180 minus sine of theta. Sine 360 is 0 times cosine of theta, so 0 minus cosine of 360, which is 1, negative 1, sine of theta. So negative sine, it's still negative sine of theta. So the formula will not change. So it's still the same, even if the depth of flow goes beyond half the diameter. So this is applicable for all situations. So likewise, so that's for theta 0 degree less than theta degrees less than 360 degrees. Cosine of theta for this situation is zero point 0.5 of the diameter minus this value, which is 0.5 d cosine of, um, this is 0.5 d, this part is 0.5 d minus d, 0.5 d minus d. So cosine of theta over 2 is 0.5 d minus d over hypotenuse 0.5 d. So this is the general expression for cosine theta when the depth of flow is below 0.5 d. Now what if the depth is above 0.5 d? So this value would be d, this will be the depth minus 0.5 d. So cosine of this angle now is 180 degrees minus theta over 2. So cosine of 180 degrees minus theta over 2 equals d minus 0.5 d over 0.5 d. So again, this is depth because this is now the depth minus 0.5 d, then divided by hypotenuse, which is 0.5 d. So cosine of 180 minus theta over 2 is cosine 180, which is negative 1, cosine of theta over 2. So this is negative cosine theta over 2 plus sine 180 sine of theta over 2 cos plus sin. So cosine 180 cosine theta over 2 plus sine 180, which is 0 sine theta over 2. So the second term is 0. So let's concentrate on cosine 180 cosine theta over 2. Cosine 180 is negative 1 times cosine of theta over 2. So this is negative cosine of theta over 2 equals d minus 0.5 d over 0.5 d. So if we multiply everything by negative 1, so this becomes cosine theta over 2. Negative 1 times quantity d minus 0.5 d will go back to 0.5 d minus d. So the simplification of this formula will still be this one. So therefore, this is the general formula in computing for theta, regardless of the depth is shallow, below 0.5 d or above 0.5 d. Then, since we cannot fit all the solutions here, we have to proceed first to the longer solution, which is because the others will be tabulated. For 41.4, let's compute the normal depth. So area is 3.6 square over 8, that's 1.62 if you simplify, times pi theta over 180 minus sine of theta. Then the perimeter is simply 0.5d radius 1.8 times central angle in degrees. So cosine theta over 2 is 0.5d, 1.8 minus d over 1.8. That's the specific formula for this case. So theta is 2 times inverse cosine of this quantity 1.8 minus d over 1.8. Then 41.4 area therefore is 3.6 square over 8 times pi theta over 180 minus sine theta. If you simplify that, that's 1.62 pi theta degrees over 180 minus sine theta. Then the perimeter is radius 0.5d, radius 1.8 times central angle in degrees. So the central angle is theta degrees, so we convert that to radians, times pi over 180. So that is reducible to pi theta over 100, where theta is in degrees. Substitute into the formula for Q, which is area to the 5/3, slope to the 1/2, over n, perimeter to the 2/3, where the slope here for uniform flow is also the slope of the channel bed because we're computing for the normal depth. So 3.4 equals 1.62 quantity pi theta over 180 minus sine theta to the 5/3 times 0.002 raised to 1/2 over n 0.015 perimeter pi theta over 100 to the 2/3. So 3.4 times 0.05 times quantity pi over 100 to the 2/3 divided by quantity 1.62 to the 5/3 times square root of 0.002. That would be 0.05081. Then what is left here is pi theta over 180 minus sine theta to the 5/3 over theta to the 2/3. So using your high-tech calculator, or for those without high-tech calculator, you will be forced to solve this by trial and error. So theta is in degrees, no? 115.74 degrees. From there, we can now compute the normal depth, which is point cosine of theta over 2 is 1.8 minus the depth is 1.8 minus 1.8. This is 1.8 cosine of theta over 2. Normal depth is 1.8 minus 1.8 cosine of theta 115.74 degrees over 2. So the normal depth is 0.8427 meters. So which will not cross the depths, the distance between depths that we are looking for, between 1 meter and 1.2 and between 2 and 2.1. But there is one more, the critical depth, on the next slide. So that's it for the normal depth. We have answered one question. First, 1 to 3 and 5 and 6 question, let's tabulate. But let's recall the formulas and the given values. So that's the area. This is cosine theta over 2, 1.8 minus d over 1.8. Perimeter, 1.8 theta degrees times pi over 180, or pi theta over 100. Then delta x for computing distance, specific energy at 1 minus specific energy at 2 over S minus SO, where the depth at 2 is treated as the downstream depth. And let's tabulate everything that are necessary here. Aside from that, let's tabulate the following. The depth, theta degrees, but not all, of course, some. Area, perimeter, hydraulic radius, mean hydraulic radius in computing for S, velocity, Q over area, mean velocity, average of the velocities at two sections, between 1 and 1.2 and between 2 and 2.1 later. Then the slope, S of the energy grade line, and mean velocity over hydraulic radius mean to the 2/3 quantity square. Velocity head, then the specific energy, which is velocity head plus depth. And aside from that, we are given Q 3.4 cubic meters per second, N 0.015, and SO 0.002. So for the depth, let's begin with 0.6, which is given. So substitute here. Theta is 2 times inverse cosine of your calculator, open quantity, 1.8 minus 0.6 over 1.8 close. Then you will get theta in degrees. Do not erase. The next depth is 1 for distance between 1 and 1.2. So in your calculator, you just replace the portion D. You set up 2 inverse cosine of open quantity 1.8 minus D, which is in this case 1 this time, over 1.8 close. Then automatic you will have theta here, 1 to the 7.22. For depth of 1.2, so all you have to do is replace in your calculator this part 1.2, and you will get 1 for 1.06 degrees. Then for 1.8, replace that by 1.8, 180 degrees, of course, half, semicircle, right? Then 2, replace this by 2, 192.76 degrees. 2.1, replace that by 2.1, you will get 199.19 degrees. Then 3, replace that by 3, you will get 263.62 degrees. Then for the area, so set up in your calculator 1.62 times open quantity pi times 96.38. So everything here must be computed, the area. So pi 96.38 over 180 minus sine of 96.38. Set up that in your calculator. You will get area here of 1.115. Then for in this situation here, you just replace theta by 127.22 in your calculator. Then this one also 122.22, you will get 2.307. Then replace 141.06, this one 141.06, you will get 2.970. Then replace that by 180, you will get 5.089. The next 192.76 for theta, 192.76, you will get 5.808. Then replace 199.19, 199.19, you will get 6.164. And lastly, replace 263.62, 263.62, you will get 9.064. The perimeter is simply pi theta over 100. This is the simplified. 1.8 over 180 is 1 over 100. So pi theta over 100. So we only consider 1, 1.2, 2, and 2.1. We don't need that for 0.6, 1. For 1.8 and 3. Just 1, 1.2, 2, and 2.1 because we need to compute S later. So for 1, substitute here, pi 127.22 divided by 100, you will get 3.997. At 1.2, pi 141.06 over 100, 4.432. Then at 2, pi 192.76 over 100, 6.056. Then at 2.1, pi 199.19 over 100, you will get 6.258. Then the hydraulic radius is simply area over perimeter. So 2.307 divided by 3.997, that's the value here, 0.5772. 2.97 only for 1, 1.2, 2, and 2.1. So 2.97 divided by 4.42, you will get 0.6701. 5.808 divided by 6.056, you will get 0.9590. And 6.164 divided by 6.258, you will get 0.9850. Then the mean hydraulic radius is simply the average of these two, 0.5772 plus 0.6701. Let's place it here in between, 0.6236. Then 0.959 plus 0.9850 divided by 2.972. Place it in between. Velocity is Q over area. Q is 3.4 divided by 1.115. So everything must be, all these depths must be filled up for velocity because we compute velocity head later. So 3.4 over 1.115 is 3.049. 3.4 divided by 2.307 is 1.474. 3.4 over 2.970, 1.145. 3.4 divided by 5.089 is 0.6681. 3.4 divided by 5.808 is 0.5854. 3.4 divided by 6.164 is 0.5516. 3.4 divided by 9.064 is 0.3751. Then the mean velocity only for 1 and 1.2 and 2 and 2.1. So 1.474 plus 1.145 divided by 2. Let's place it in between 1.3095. Then 0.5854 plus 0.5516. Let's place it here, 0.5685. Then we can now solve the slope. So in your calculator, quantity 0.015 times 1.3095 only for this part, divided by 0.6236 to the 2/3, then close quantity square. So the value is 0.000743. Then here, 0.015, quantity 0.015 times 0.5685 divided by 0.972 to the 2/3, close square. So it will be 0.0000407552. Then for the velocity head, 3.049 square divided by 19.62, 0.4738, 1.474 square. In your calculator, you just replace the squared part. 1.474 square divided by 19.62.1107. Replace 1.145 square, so 0.06682. 0.6681 square divided by 19.62, 0.02275. 0.5854 square divided by 19.62, 0.01747. 0.5516 square over 19.62, 0.01551. Then 0.3751 square over 19.62 is 0.007171. Then we can now compute the specific energy. This is 0.4738 plus depth 0.6, 1.0738, because we are asked in the first question the specific energy for depths of 0.6, 1.2, 1.8, and 3. So that's 1.0738 meters for depth of 0.6. For depth of 1, because we need this also, as this is E sub 1 for distance between 1 and 1.2. So 0.1107 plus 1, 1.1107, but not highlighted. At 1.2, it will be highlighted. 1.06682 plus 1.2, 1.2668. Then at 1.8, highlighted also 0.02275 plus 1.8, 1.8228. 0.01747 plus 2, 2.0175. 0.01551 plus 2.1, 2.1155. Then 0.007171 plus 3, 3.0072. Round off. So we notice that the specific energy, as the depth increases somewhere here, it also increases. Therefore, we have an idea, or given the idea that the critical depth where specific energy is minimum, of course somewhere here at this depth. So it is between 0.6 and 1. Now it will undergo so many trials before you can proceed with you can determine the critical depth. So I'll just consider 3 values or 4. Let's begin with 0.735. After, of course, so many trials, so we'll just consider this. I'm not saying that that's really the value. I tried 6 values before I got the almost correct value. So 0.735, let's begin with this. So let's compute for theta. Again, 2 inverse cosine of 1.8 minus 0.735 or 1.8, close in your calculator. So 107.45 degrees. The area, substitute here, 1.62. So let's solve for theta first. Next is 0.74. So replace this by 0.74 in your calculator, you'll get 107.84. Then 0.745, replace 0.745, you will get 108.24. And for the area, 1.62 quantity pi, 107.45 over 180 minus sine of 107.45, 1.493. Then replace 107.84, 107.84, you will get area of 1.507. Replace this by 108.24, 108.24, the area is 1.522. Then for the velocity, 3.4 over 1.493, 2.277. Then 3.4 over 1.507 is 2.256. 3.4 over 1.522 is 2.234. We don't need this because we only need for 1.2 and 1 and 1.22 and 2.1. So we also don't need this part. So just the velocity head. So 2.277 squared over 19.62 is 0.2643. 2.256 squared over 19.62 is 0.2594. 2.234 squared over 19.62 is 0.2544. Then for the specific energy, 0.2643 plus 0.735 is 0.993. 0.2594 plus 0.74 is 0.9994. So it's very close. 0.2544 plus 0.745 is also 0.9994. So far, this is the least specific energy. So let's try 0.73. So there's no more space. Let's just put it here. When depth is 0.73, you compute for theta again. Replace this by 0.73. Theta is 107.05. Then replace 107.05, 107.05. The area is 1.478. Then the velocity, 3.4 over 1.478, 2.300. Then velocity head, 2.3 square over 19.62, 0.2696. Plus 0.73 is 0.9996. So it's greater. Therefore, this value is the minimum specific energy to 3 decimal places. Therefore, we have found the critical depth, which is 0.735. And 0.735 is away from 1 and 1.2. That it does not cross, and it does not cross also between 2 and 2.1. So that our solution for delta x between these two depths will be valid. So that's it. We have found the normal depth, the critical depth, and the specific energies. So the last question would be the distance between two sections. So by the way, we have to verify, we have to compare q squared over g, which is 3.4 squared over 9.81, it is 1.178. And area critical cube over b, because that's the critical depth formula. This value q squared over g and area cube over top width must be almost close, or supposedly close, but because of rounding of values, then we'll just expect that they're close or not too close. As long as they're close, then we are validating this answer for critical depth. So area critical at 0.735 is 1.493. It's now the top width. So can you remember the triangle? So the top width is below. So it is 1.8 sine of theta over 2 times 2. So 2 times 1.8 sine of theta over 2, where theta is 107.45 divided by 2, so 2.902 meters. That's the top width of the water surface. Then area critical cube over top width is area critical is 1.493 cube over top width 2.907, so it is 1.147. That's close to 1.178. This is 1.18. This is 1.15. So it's acceptable. So let's validate the answer of 0.735. In fact, it will be very close if the answer is 0.74, but based on our calculation, the one that gives minimum specific energy is 0.9993, although they're very close. But either way, this is still acceptable if your answer is 0.74 meter for critical depth. Anyway, that's matter of 0.005. So, and this is not exact science, of course, affected by natural factors. So 0.735 meters, 0.74, that's still acceptable answer for the critical depth. Then for the distance, last delta x is E1 minus E2 over S minus SO, where the deeper depth, 1.2, is considered the downstream depth. Then if this is positive, our assumption is correct. So E sub 1 would be 1.1107, E sub 2 would be 1.2668. Then S is 0.000723 minus SO 0.002. So everything is set up. You just substitute 1.1107 minus 1.2668 divided by 0.000723 minus 0.002. The answer is positive. So delta x is 122.4. with 1.2 meters as downstream depth. So that's the answer. Then distance between 2 and 2.1, delta x is 2.0175. So 2.1 as downstream depth. So delta x is 2.0175 minus 2.1155 over 0.00007552 minus 0.002. So the answer is still positive, 50.92 with 2.1 meter as downstream depth. So that's all, and I hope that you learn a lot for this solution here. This is a very comprehensive problem, and the section is circular that the critical depth is difficult to determine, but because of the definition that critical depth occurs where specific energy is minimum, we're able to find it. And the normal depth is not so challenging, but it requires high-tech calculator for us to compute for the theta. And with the formula set up and the solution tabulated, everything will be fine.